At IBM, we define AI as anything that makes machines act more intelligently. We like to think of AI as augmented intelligence. We believe that AI should not attempt to replace human experts, but rather extend human capabilities and accomplish tasks that neither humans nor machines could do on their own. The internet has given us access to more information faster. Distributed computing and IoT have led to massive amounts of data, and social networking has encouraged most of that data to be unstructured. With augmented intelligence, we are putting information that subject matter experts need at their fingertips, and backing it with evidence so they can make informed decisions. We want experts to scale their capabilities and let the machines do the time-consuming work. How do we define intelligence? Human beings have innate intelligence, defined as the intelligence that governs every activity in our body. This intelligence is what causes an oak tree to grow out of a little seed and an elephant to form from a single-celled organism. How does AI learn? The only innate intelligence machines have is what we give them. We provide machines the ability to examine examples and create machine learning models based on the inputs and desired outputs. And we do this in different ways, such as supervised learning, unsupervised learning, and reinforcement learning, about which you will learn in more detail in subsequent lessons. Based on strength, breadth, and application, AI can be described in different ways. Weak or narrow AI is AI that is applied to a specific domain. For example, language translators, virtual assistants, self-driving cars, AI-powered web searches, recommendation engines, and intelligent spam filters. Applied AI can perform specific tasks but not learn new ones, making decisions based on programmed algorithms and training data. Strong AI, or generalized AI, is AI that can interact and operate a wide variety of independent and unrelated tasks. It can learn new tasks to solve new problems, and it does this by teaching itself new strategies. Generalized intelligence is the combination of many AI strategies that learn from experience and can perform at a human level of intelligence. Super AI, or conscious AI, is AI with human-level consciousness, which would require it to be self-aware. Because we are not yet able to adequately define what consciousness is, it's unlikely that we will be able to create a conscious AI in the near future. AI is the fusion of many fields of study. Computer science and electrical engineering determine how AI is implemented in software and hardware. Mathematics and statistics determine viable models and measure performance. Because AI is modeled on how we believe the brain works, psychology and linguistics play an essential role in understanding how AI might work, and philosophy provides guidance on intelligence and ethical considerations. While the science fiction version of AI may be a distant possibility, we already see more and more AI involved in the decisions we make every day. Over the years, AI has proven to be useful in different domains, impacting the lives of people and our society in meaningful ways.
There's a lot of talk about artificial intelligence these days. How do you define, or what does AI mean for you?
There is a lot of talk and there's a lot of definitions for what artificial intelligence is. So one of them is about teaching the machines to learn and act and think as humans would. Another one, another dimension is really about how do we get the machines to, how do we impart more of a cognitive capabilities on the machines and sensory capabilities. So it's about analyzing images and videos. It's about natural language processing and understanding speech. It's, it's about pattern recognition and so on and so forth. So the third axis is more around creating a technology that's able to, in some cases, replace what humans do. I'd like to think of this augmented what humans do. To me personally, the most important part of definition for artificial intelligence is about imparting the ability to think and learn on the machines. To me, that's what defines artificial intelligence.
AI is the application of computing to solve problems in an intelligent way using algorithms. And so what is an intelligent way? Well, an intelligent way may be something that mimics human intelligence, or it may be a purely computational approach, an optimization approach, but something that manipulates data in a way to get non-obvious results out, I think is what I would classify as being artificially intelligent.
I would define AI as a tool that uses a computer to complete a task automatically with very little to no human intervention.
To me, AI is really a complex series of layers of algorithms that do something with the information that's coming into it.
Artificial intelligence is a set of technologies that allows us to extract knowledge from data. So it's any kind of system that learns or understands patterns within that data and can identify them and then reproduce them on new information.
Artificial intelligence is not the kind of simulating human intelligence that people think it is. It's really not about intelligence at all. But I think another word that describes AI more accurately today is machine learning. And the reason I say that is because machine learning technology is all about using essentially mathematics on computers in order to find patterns in data. Now, this data can be structured or unstructured, and the only difference between machine learning and the technologies that came before it is instead of us as humans having to manually hard code these patterns and these conditions into computers, they're able to find these patterns on their own by using math. That's really the only difference here. So what I'd say artificial intelligence is it's a set of mathematical algorithms that enable us to have computers find very deep and patterns that we may not have even known exist without us having to hard code them manually.
Hi, Tanmay. Welcome. And tell us, how old are you?
I'm 15 years old.
Great. And how did you get started in technology and AI?
Sure. So I've been working with technology for over 10 years now. It all started back when I was around 5 years old because my dad used to work as a computer programmer. And watching him program almost all day was so fascinating to me that I really wanted to find out more. I wanted to find out how computers could do really anything that they did, whether that be displaying my name on the screen or adding two numbers or really anything of that sort. It was like magic to me at that age. And so my dad introduced me to the world of programming, and I had been working with code. I submitted my first iOS application and more. But when I was around 10 years old, I started to feel like technology wasn't as fun as it used to be for me. You know, technology wasn't as exciting as it used to be for one simple reason. It's because technology was very rigid. You code something in and it immediately starts to become obsolete. It never adapts. It never changes to new data, new users, new circumstances they create. But when I was 11 years old, I actually stumbled upon a documentary on IBM Watson playing and winning the Jeopardy game show back in 2011. And so, of course, that immediately fascinated me as to how a computer can play Jeopardy. And so I went ahead, did a little bit more research, found out that IBM provides Watson's individual components as APIs on the cloud. I did a little bit more research, started to create my very first sort of cognitive applications, and I also created tutorials on my YouTube channel on how others can also leverage the IBM Watson APIs. And so really ever since I was 11 years old, I've been working with machine learning technology through numerous different services like IBM Watson.
That's awesome. So what does AI mean for you?
Now, really what AI means to me, before I get to that, before I can explain what AI is to me, I think it's first important to understand really what others like to think of AI as. Now, a lot of people have this very sort of split, this sort of very sort of bipolar response to machine learning, or AI, as people call it. Some people are like, yes, this is the greatest technology of all time. And some people are like, this will be the downfall of humanity. And I'd say that neither of those responses would be correct. And the reason I say that is because machine learning technology is technology. It's very advanced technology. It helps us do things that we never could have done before. But it's just that. It's technology. And artificial intelligence and machine learning is something that people have been working on mathematically since even before computers were a thing. Machine learning technology is not new at all. In fact, it's existed, the very fundamentals at least, for many decades before I was even born. But the thing is, Machine learning technology, or at least, for example, the basic perceptron and these sorts of mathematical techniques have existed since even before computers or calculators became popular. And so when we were creating these sorts of machine learning concepts in AI, and we started to create literature and movies on the future of technology and computers, we barely had any idea of not only where technology would go in the future, but also what technology really is. And because of that, people have this very common misconception of artificial intelligence being the human mind within a computer, the human intelligence simulated wholly within a computer. But that couldn't be farther from the truth. Machine learning, or AI, is not simulating a human mind. But what it does try and do is it tries to open up new doors for computers. It tries to enable computers to understand certain kinds of data that they couldn't have understood before. So, like, for example, if you take a look at what we as humans are so special at, the fact that we can understand natural language. In fact, we are the only animal to have such a complex ability of being able to communicate in natural language. Even if there's something that I have not directly witnessed or seen or heard evidence for, I can still describe that imaginative concept to you. That is actually really wonderful. And we're also great at understanding raw auditory data. I mean, imagine your brain is actually taking vibrations of air molecules and converting that to thoughts. That's really amazing. And you're also great at processing visual data. Like when you look at someone's face, the fact that you can instantly recognize them. When you look at someone's eyes, you can tell exactly where they're looking. That's really an amazing ability. And these are things that computers cannot do because they are fundamentally limited to mathematics. They can only understand numbers and mathematical operations. But by using machine learning technology, you can actually take these mathematics and use them to understand patterns in vast amounts of both structured and unstructured human data. The only difference here is that before, we as humans would manually construct these patterns and these conditions, whereas now it's done automatically for us, at least mostly automatically, by techniques like gradient descent and calculus. So machine learning technology is a more accurate term for what AI really is today and will be in the future. And of course, artificial intelligence isn't meant to replace us, because on a fundamental level, it is a completely different thing than a human brain.
Welcome to Generative AI Overview and Use Cases. After watching this video, you'll be able to define generative AI and describe its significance, and explain different use cases of generative AI. Artificial intelligence, AI, is defined as augmented intelligence that enables experts to scale their capabilities while machines handle time-consuming tasks like recognizing speech, playing games, and making decisions. On the other hand, generative artificial intelligence, or Gen AI, is an AI technique capable of creating new and unique data, ranging from images and music to text and entire virtual worlds. Unlike conventional AI models that rely on predefined rules and patterns, generative AI models use deep learning techniques and rely on vast data sets to generate entirely new data with various applications. A generative AI model can also use LLM, large language model, a type of artificial intelligence based on deep learning techniques designed to process and generate natural language. For instance, generative AI can develop new and more powerful LLM algorithms and architectures, resulting in more accurate or efficient natural language processing and generation capabilities. Alternatively, a generative AI can design and incorporate LLM into a larger, more advanced AI system to perform various advanced tasks such as decision-making, problem-solving, and creative work. Generative AI encompasses various AI technologies and the idea of developing AI systems. Although more about generative AI will soon unfold, the following benefits already make generative AI a strategic technology. 1. Creativity and innovation. 2. Cost and time savings. 3. Personalization. 4. Scalability. 5. robustness, and 6. Exploration of new possibilities. Let's look at some diverse use cases of generative AI. 1. In the field of healthcare and precision medicine, generative AI can support physicians in identifying genetic mutations responsible for patients' illnesses and providing tailored treatments. It can also produce medical images, simulate surgeries, and predict new drug properties to aid doctors in practicing procedures and developing treatments. 2. In agriculture, generative AI can optimize crop yields and create more robust plant varieties that can withstand environmental stressors, pests, and diseases. 3. In biotechnology, generative AI can aid in the development of new therapies and drugs by identifying potential drug targets, simulating drug interactions, and forecasting drug efficacy. 4. In forensics, generative AI can help solve crimes by analyzing DNA evidence and identifying suspects. 5. In environmental conservation, generative AI can support the protection of endangered species by analyzing their genetic data and suggesting breeding and conservation strategies. 6. In creative fields, generative AI can produce unique digital art, music, and video content for advertising and marketing campaigns, and generate soundtracks for films or video games. 7. In gaming, generative AI can create interactive game worlds by generating new levels, characters, and objects that adapt to player behavior. 8. In fashion, generative AI can design and produce virtual try-on experiences for customers and recommend personalized fashion choices based on customer behavior and preferences. 9. In robotics, generative AI can design new robot movements and adapt them to changing environments, enabling them to perform complex tasks. 10. In education, generative AI can create customized learning materials and interactive learning environments that adjust to students' learning styles and paces. 11. In data augmentation, generative AI can produce new training data for machine learning models, enhancing their accuracy and performance. In this video, you learned that generative AI is an AI technique capable of creating new and unique data. It outperforms traditional AI models in terms of creativity, cost and time savings, personalization, scalability, robustness, and exploration of new possibilities. Generative AI has the potential to transform various industries and improve people's lives and generate newer and impossible data and experiences. It can be used for anything to perform a wide range of tasks similar to the flexibility and adaptability of human intelligence.
AI is here to stay, with the promise of transforming the way the world works. According to a study by PwC, $16 trillion of GDP will be added between now and 2030 on the basis of AI. This is a never-before-seen scale of economic impact, and it is not just in the IT industry. It impacts virtually every industry and aspect of our lives. AI means different things to different people. For a video game designer, AI means writing the code that affects how bots play and how the environment reacts to the player. For a screenwriter, AI means a character that acts like a human with some trope of computer features mixed in. For a data scientist, AI is a way of exploring and classifying data to meet specific goals. AI algorithms that learn by example are the reason we can talk to Watson, Alexa, Siri, Cortana, and Google Assistant, and they can talk back to us. The natural language processing and natural language generation capabilities of AI are not only enabling machines and humans to understand and interact with each other, but are creating new opportunities and new ways of doing business. Chatbots powered by natural language processing capabilities are being used in healthcare to question patients and run basic diagnoses like real doctors. In education, they are providing students with easy-to-learn conversational interfaces and on-demand online tutors. Customer service chatbots are improving customer experience by resolving queries on the spot and freeing up agents' time for conversations that add value. AI-powered advances in speech-to-text technology have made real-time transcription a reality. Advances in speech synthesis are the reason companies are using AI-powered voice to enhance customer experience and give their brand its unique voice. In the field of medicine, it's helping patients with Lou Gehrig's disease, for example, to regain their real voice in place of using a computerized voice. It is due to advances in AI that the field of computer vision has been able to surpass humans in tasks related to detecting and labeling objects. Computer vision is one of the reasons why cars can steer their way on streets and highways and avoid hitting obstacles. Computer vision algorithms detect facial features in images and compare them with databases of face profiles. This is what allows consumer devices to authenticate the identities of their owners through facial recognition, social media apps to detect and tag users, and law enforcement agencies to identify criminals in video feeds. Computer vision algorithms are helping automate tasks, such as detecting cancerous moles in skin images or finding symptoms in X-ray and MRI scan. AI is impacting the quality of our lives on a daily basis. There is AI in our Netflix queue, our navigation apps, keeping spam out of our inboxes, and reminding us of important events. AI is working behind the scenes, monitoring our investments, detecting fraudulent transactions, identifying credit card fraud, and preventing financial crimes. AI is impacting healthcare in significant ways by helping doctors arrive at more accurate preliminary diagnoses, reading medical imaging, finding appropriate clinical trials for patients. It is not just influencing patient outcomes, but also making operational processes less expensive. AI has the potential to access enormous amounts of information, imitate humans, even specific humans, make life-changing recommendations about health and finances, correlate data that may invade privacy, and much more.
Can you talk about some of the applications of AI?
There's all kinds of different applications, obviously. There's healthcare, there's finance. The one that's closest to my heart, of course, is robotics and automation, where the AI technologies really help us to improve our abilities to perceive the environment around the robot and to make plans in unpredictable environments as they're changing.
There's a great book out by an author who's Kevin Kelly, and he's an editor for the Wired magazine. He's written a great book about technologies that are going to be changing and shaping our world, specifically 12 technologies. And he's got a fantastic definition in the book about, specifically how AI is going to permeate our everyday lives. And it's all summarized in one excellent quote. So he says that the business cases for the next 10,000 startups are easy to predict. I have X, and I will add AI to my X. The way I understand that is, is basically a notion that AI in one shape, way, or form, in any shape, way, or form, is going to permeate every aspect of human endeavor. Everything we do, everything we touch is going to be enhanced by AI. We get great benefit from taking any device, any machine, and make it just a little bit smarter. The benefit of that is, just adding a bit of smarts to it, a bit of intelligence to it, is exponential in its benefit.
So we work a lot with some really fun applications of AI. We do a couple of different things in the lab that I run. We work on self-driving vehicles as one aspect, so autonomy for self-driving, which requires a lot of AI for the vision systems, for the navigational intelligence, for the planning and control aspects of the car. We do that, and we also have a large research program in what are called collaborative robotics, or cobots. So robots that are designed to work in and around and with people. And that presents a lot of challenges because we want the robots to act intelligently and to interface with humans in a way that is natural. And that requires understanding how people behave, which requires intelligence. In addition to those, there are a myriad of other applications, drug discovery, medical treatments for cancer and other diseases. So a bunch of extremely exciting applications.
I mean, I think the general use of AI so far has been taking large data sets and making sense of them. and doing some sort of processing with that data in real time. That's what we've been doing, and that's what we've seen most effective in terms of creating some sort of larger scale impact in healthcare beyond just having a siloed device. And we've been seeing that across the board, across the whole healthcare spectrum.
We use AI all the time, and a lot of the times we're not even aware of it. We use AI every time we type in a search query on a search engine, every time we use our GPS, or every time we use some kind of voice recognition system.
I'd like to focus on a particular segment of AI, if that's okay, around computer vision, because it's just particularly fascinating to me. Now, when we think of computer vision, so we're looking at AI in ways to help augment or to help automate or to help train computers to do something that's already very difficult to train humans to do. When it comes to the airport, trying to find weapons within luggage through the X-ray scanner, that could be difficult to do. No matter how much you train someone, that could be very difficult to identify. But with computer vision, it can help to automate, help to augment, help to flag certain X-ray images so that maybe even humans can just take a look at a filtered set of images, not all of the images, right? So computer vision is very disruptive. And so there's many ways in which computer vision can really help to augment the capabilities of humans in lots of different industries.
Now, applications of AI are really all around us. There's no limit to really what we're doing with artificial intelligence. When you do practically anything on any technology, you're most probably using some form of what we call machine learning or artificial intelligence. Like, for example, when you check your email, doing something as simple as checking your email. Spam filtering has been done for years with machine learning technology. More recently, Google came out with their features that enable you to do smart email composition, so you can actually have text written for you on the fly as you're writing your email. Your subjects are automatically written as well. It'll recommend to you who you should be sending the email to, see if you've missed someone. All of these things are powered by machine learning. But some of the main areas where I believe machine learning technology can make an impact are in the fields of healthcare and education.
Can you give some specific examples of applications of AI?
Certainly. So we have a fairly large collaborative robotics program. And so the cobots we work on are primarily targeted at the moment at manufacturing applications, manufacturing, warehousing, logistics, these types of applications where normally you may have a person doing a job that is it can be dull, it can be dangerous, and having robotic support or having a robot actually do the job may make it much safer, more efficient, and just more effective overall. So we work on a lot of those types of applications, particularly where the robots are trying to interface directly with people, as I said. So the robot may help an individual to lift a heavy container or help to move items on a shelf for stocking purposes. So all these kinds of applications where I think we'll see collaborative robots move first, and then hopefully one day maybe into your home to help you with the laundry and the dishes in the kitchen, hopefully.
For example, in oil and gas, there's a company, a pretty large oil and gas company called the Abu Dhabi National Oil Company. And what they do is, well, I should say, one of the problems that any kind of oil company has to deal with is, where is the best place for them to drill for oil, right? So they have to find these rock samples of all these different places, for this place, and then this place, and that place, and maybe hundreds of different places for them to drill oil. And from these rock samples, now you have all these, fine sheets of rock, and maybe hundreds or thousands of them. And it's up to these oil companies to be able to classify these using their trained and expert geologists. But to train geologists to properly classify these sheets of rock can be quite difficult. It could be time consuming, could cost a lot of money as well. So one way to help augment the capabilities of humans is to be able to use computer vision to classify these rock samples, to be able to identify which of these locations are the best to drill for oil. And that's in oil and gas.
Imagine before this, if there was a very, very rare form of cancer experienced by a doctor in Dubai, and if there were another case in New Zealand, how do you think they would have actually figured out that, hey, we're both dealing with this very rare case, let's work together? That wouldn't have been possible in the past. But now with machine learning technology, being able to aggregate knowledge from so many different sources into one centralized cloud and understand it and provide that information in an accessible, intuitive, implicit way, now that New Zealand doctor can actually go ahead and use this machine learning technique to say, hey, just a few days ago there was a doctor with a very similar case, even though it may not be the exact same thing.
Sure. So we work with a number of startups and a number of enterprises, and I'll just bring a couple of examples. So one that I like to talk quite a bit about is a company out in California called Echo Devices. And what they've done is they've taken a simple device, which is stethoscope, something we see around the neck of every physician, a nurse, and healthcare professional. And they've taken that device and they've basically have transformed it into a digital device by cutting the tube on a stethoscope, inserting a digitizer into it that takes an analog sound, transforms it into a digital signal, amplifies it in the process, makes it a lot easier for people to hear because it's amplified sound, the sound of your heart or your lungs working. But what it also allows us to do is it allows us to take that digital signal and send it via Bluetooth to a smartphone. And once it's on a smartphone, they're able to graph it, which allows the physician to better understand, not just through audio data, but through an actual graph of how your heart is working. But because that information is now captured in the digital world, it can now be sent to a machine learning algorithm, and that's what they do. And a machine learning algorithm can actually now learn from that, apply a previous learnings from the human doctors, cardiologist, and now assist a physician who is using the device in their current diagnosis. So this is, it's basically, it's not replacing a physician in any way, shape, or form. It is assistive technology, which is taking the learnings of the previous generations of the humans, human cardiologists, and helping in the diagnosis in the current state. To me, that's a perfect example of taking the X, which is in this particular case is a stethoscope, and then adding AI to that X. And they have a really nifty name for that. They call it Shazam for heartbeats.
Can you talk about AI in action?
To give an example of, say, machine learning in action today, how companies have actually implemented it, there's one example that I always love to go back to, and it is the example of Woodside Energy, a company in the Australia-New Zealand region. Now, originally, they actually contacted IBM because they wanted IBM to be able to create essentially a system that can understand the different documents and the research that their engineers come up with, and have Watson understand that and essentially replace some of the engineers on their team. And, IBM actually went ahead and built the application. It worked. Watson was able to understand that unstructured content, but they never ended up replacing any of their engineers. Instead, they actually ended up hiring more engineers because now they realized that two things. First of all, the barrier of entry for each engineer is now lower, and knowledge can now be shared more effectively among the teams. Because now, instead of research being written and put into an archive drawer where it's never seen again, Watson's ingesting that data, understanding it, and providing it to whoever needs it, or whoever Watson thinks would need that data.
So if you imagine, in these TV shows and in these movie scenes as well, you have, sometimes, someone's looking for a particular suspect in this particular, traffic intersection or whatnot. They've passed through this intersection, and there's, of course, some cameras around. And so we have the security guard, maybe, try to look through hours and hours, dozens and hundreds of hours of footage, maybe at 10x speed, and trying to find that particular black SUV or that green, car. And then as soon as they find it, at the end of the episode or whatnot, then they say, aha, we found that person. But if you had some sort of computer vision algorithm running on this video footage the entire time, then you wouldn't have a need for some person to have to manually watch through hours and hours of footage.
Our specific use case is actually triggering new neural pathways in the brain to form. As you can imagine, there's a lot of information that happens there between the connection of how your body functions and how your brain functions, and what parts of the brain are damaged, what parts of the brain aren't damaged, and how you're actually moving the person, or how you're triggering certain things in the human body to happen in order for new neural pathways to form. So what we've done is actually we've created massive data sets of information of how people move and how that responds to different areas of the brain. And through that information, we're able to trigger specific movements with a robotic device, which in turn creates these neural pathways to form in the brain, and therefore recovering the person who's suffered a neurological trauma.
I remember that morning going to the lab, and I was thinking, this is it. This is the last Jeopardy game.
It became real to me when the music played and Johnny Gilbert said, from IBM Research in Yorktown Heights, New York, this is Jeopardy. And I just went...
And here it is, one day. This is the culmination of all this work. To be honest with you, I was emotional.
Watson. What is issue? You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
The Double Jeopardy round of the first game, I thought was phenomenal.
Watson went on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
You are right, and with that, you move to $36,681. Now we come to Watson, who is Bram Stoker, and the wager? Hello, 17,973, and a two-day total of 77,147.
We won Jeopardy.
They're very justifiably proud of what they've done. I would have thought that technology like this was years away, but it's here now. I have the bruised ego to prove it.
I think we saw something important today.
Wow, wait a second. This is history.
The 60th Annual Grammy Awards, powered by IBM Watson.
There's a tremendous amount of unstructured data that we process on Grammy Sunday.
Our partnership with the Recording Academy really is focused on helping them with some of their workflows for their digital production.
My content team is responsible not only for taking all of this raw stuff that's coming in, but curating it and publishing it. You're talking about 5 hours of red carpet coverage with 5,000 artists making that trip down the carpet with 100,000 photos being shot.
For the last 5 hours, Watson has been using AI to analyze the colors, patterns, and silhouettes of every single outfit that has passed through. So we've been able to see all the dominant styles and compare them to Grammy shows in the past.
And Watson's also analyzing the emotions of Grammy-nominated song lyrics over the last 60 years. Get this, it can actually identify the emotional themes in music and categorize them as joy, sadness, and everything else in between. It's very cool.
Fantasy sports are an incredibly important and fun way that we serve sports fans. Our fantasy games drive tremendous consumption across ESPN digital properties, and they drive tune-in to our events and studio shows. But our users have a lot of different ways they can spend their time. So we have to continuously improve our game so they choose to spend that time with us.
This year, ESPN teamed up with IBM to add a powerful new feature to their fantasy football platform.
Fantasy football generates a huge volume of content. Articles, blogs, videos, podcasts. We call it unstructured data, data that doesn't fit neatly into spreadsheets or databases. Watson was built to analyze that kind of information and turn it into usable insights.
We trained Watson on millions of fantasy football stories, blog posts, and videos. We taught it to develop a scoring range for thousands of players, their upsides and their downsides. And we taught it to estimate the chances a player will exceed their upside or fall below the downside. Watson even assesses a player's media buzz and their likelihood to play.
This is a big win for our fantasy football players. It's one more tool to help them decide which running back or QB to start each week. And it's a great complement to the award-winning analysts our fans rely on. As with any machine learning, the system gets smarter all the time. That means the insights are better, which means our users can make better decisions and have a better chance to win their matchup every week. The more successful our fantasy players are, the more time they'll spend with us.
The ESPN-IBM partnership is a great vehicle to demonstrate the power of enterprise-grade AI to millions of people. And it's not hard to see how the same technology applies to real life. There are thousands of business scenarios where you're assessing value and making trade-offs. This is what the future of decision-making is going to look like. Man and machine working together, assessing risk and reward, working through difficult decisions.
This is the same technology IBM uses to help doctors mine millions of pages of medical research. And investment banks find market-moving insights.
Welcome to Generative AI Applications. After watching this video, you'll be able to list various applications of generative AI and explore the uses for each application. Generative AI has emerged as a powerful technology that enables software applications to create, generate, and simulate new content, enhancing their capabilities and providing unique experiences. Unlike traditional software that follows predefined rules and algorithms, generative AI leverages machine learning and deep learning techniques to learn patterns and generate original content based on the knowledge it has acquired during training. Due to its potential to create new, personalized content that would have been impossible to create otherwise, generative AI has been used in various fields, leading to the development of numerous engaging and well-liked applications. Some popular applications of generative AI in action include 1. Generative Pre-trained Transformers, or GPT, is a family of large language models developed by OpenAI that are capable of producing human-like text. GPT 3.5 and GPT 4 are iterations in this family of models with more futuristic models under development. It has a wide range of applications, including chatbots powered by GPT, like ChatGPT, automated journalism, and even creative writing. 2. ChatGPT is a chatbot or conversational AI tool by OpenAI that enables users to have text-based conversations with the underlying language model, GPT. Trained on diverse internet text, it generates human-like responses, providing information, answering questions, assisting with tasks, engaging in creative writing, and offering suggestions across various subjects. 3. Bard is an AI-powered writing assistant from Google that aims to assist users in producing high-quality writing for communicational documents like emails and social media posts. Bard generates text using large language model called Lambda, language model for dialogue applications, and can adjust to the user's preferences for style and tone. 4. Watson X from IBM is an AI and data platform comprising watsonx.ai for model deployment, watsonx.data for scalable analytics, and watsonx.governance for responsible AI workflows. It helps build, deploy, and manage AI applications at scale, enhancing the impact of AI across your organization. 5. Deep Dream is a generative model that can generate surreal and psychedelic images from real-life images. It has been used in art and entertainment, producing some one-of-a-kind and visually stunning images. 6. StyleGAN is a generative model capable of producing high-quality images of faces that do not exist in reality. It's been used in a variety of applications, including creating realistic video game avatars and simulating human faces for medical research. 7. AlphaFold is a generative model that can predict protein structure. It has the potential to transform drug discovery and make it possible to develop more effective treatments for diseases. 8. Magenta is a Google project that creates music and art using generative AI. It has yielded some intriguing and impressive results, such as a piano duet performed by a human and an AI-generated piano. 9. Google AI's Palm 2 is a powerful LLM trained on a dataset 10 times larger. It excels in understanding nuances, generating coherent text in code, translating, and answering questions. Ongoing development promises to revolutionize human-computer interactions, enhancing accuracy, efficiency, creativity, and communication. 10. GitHub Copilot is an AI-powered coding assistant developed by OpenAI and GitHub that is designed to help developers write code more efficiently. It uses a deep learning algorithm to analyze code and generate suggestions for the developer, such as auto-completing code snippets or suggesting functions based on the context of the code. Generative AI is a rapidly evolving space and is expected to grow dramatically in the coming years. Though there are certain ethical concerns about generative AI, including potential misuse of AI-generated content and implications for intellectual property and copyright laws. In this video, you learned that generative AI enables applications to create, generate, and simulate new content. It leverages ML and deep learning techniques to learn patterns and generate original content. And some applications of Gen AI include GPT-4, ChatGPT, Bard, GitHub Copilot, and Palm 2.
AI is at the forefront of a new era of computing, cognitive computing. It's a radically new kind of computing, very different from the programmable systems that preceded it, as different as those systems were from the tabulating machines of a century ago. Conventional computing solutions, based on the mathematical principles that emanate from the 1940s, are programmed based on rules and logic intended to derive mathematically precise answers, often following a rigid decision tree approach. But with today's wealth of big data and the need for more complex evidence-based decisions, such a rigid approach often breaks or fails to keep up with available information. Cognitive computing enables people to create a profoundly new kind of value, finding answers and insights locked away in volumes of data. Whether we consider a doctor diagnosing a patient, a wealth manager advising a client on their retirement portfolio, or even a chef creating a new recipe, they need new approaches to put into context the volume of information they deal with on a daily basis in order to derive value from it. These processes serve to enhance human expertise. Cognitive computing mirrors some of the key cognitive elements of human expertise, systems that reason about problems like a human does. When we as humans seek to understand something and to make a decision, we go through 4 key steps. First, we observe visible phenomena and bodies of evidence. Second, we draw on what we know to interpret what we are seeing to generate hypotheses about what it means. Third, we evaluate which hypotheses are right or wrong. Finally, we decide, choosing the option that seems best and acting accordingly. Just as humans become experts by going through the process of observation, evaluation, and decision-making, cognitive systems use similar processes to reason about the information they read, and they can do this at massive speed and scale. Unlike conventional computing solutions, which can only handle neatly organized, structured data, such as what is stored in a database, cognitive computing solutions can understand unstructured data, which is 80% of data today. All of the information that is produced primarily by humans for other humans to consume. This includes everything from literature, articles, research reports, to blogs, posts, and tweets. While structured data is governed by well-defined fields that contain well-specified information, cognitive systems rely on natural language, which is governed by rules of grammar, context, and culture. It is implicit, ambiguous, complex, and a challenge to process. While all human language is difficult to parse, certain idioms can be particularly challenging. In English, for instance, we can feel blue because it's raining cats and dogs, while we're filling in a form someone asked us to fill out. Cognitive systems read and interpret text like a person. They do this by breaking down a sentence grammatically, relationally, and structurally, discerning meaning from the semantics of the written material. Cognitive systems understand context. This is very different from simple speech recognition, which is how a computer translates human speech into a set of words. Cognitive systems try to understand the real intent of the user's language and use that understanding to draw inferences through a broad array of linguistic models and algorithms. Cognitive systems learn, adapt, and keep getting smarter. They do this by learning from their interactions with us and from their own successes and failures, just like humans do. Before we deep dive into how AI works and its various use cases and applications, let's differentiate some of the closely related terms and concepts of AI. Artificial intelligence, machine learning, deep learning, and neural networks. These terms are sometimes used interchangeably, but they do not refer to the same thing. Artificial intelligence is a branch of computer science dealing with the simulation of intelligent behavior. AI systems will typically demonstrate behaviors associated with human intelligence, such as planning, learning, reasoning, problem-solving, knowledge representation, perception, motion, and manipulation, and to a lesser extent social intelligence and creativity. Machine learning is a subset of AI that uses computer algorithms to analyze data and make intelligent decisions based on what it has learned, without being explicitly programmed. Machine learning algorithms are trained with large sets of data and they learn from examples. They do not follow rules-based algorithms. Machine learning is what enables machines to solve problems on their own and make accurate predictions using the provided data. Deep learning is a specialized subset of machine learning that uses layered neural networks to simulate human decision-making. Deep learning algorithms can label and categorize information and identify patterns. It is what enables AI systems to continuously learn on the job and improve the quality and accuracy of results by determining whether decisions were correct. Artificial neural networks, often referred simply as neural networks, take inspiration from biological neural networks, although they work quite a bit differently. A neural network in AI is a collection of small computing units called neurons that take incoming data and learn to make decisions over time. Neural networks are often layered deep and are the reason deep learning algorithms become more efficient as the datasets increase in volume, as opposed to other machine learning algorithms that may plateau as data increases. Now that you have a broad understanding of the differences between some key AI concepts, there is one more differentiation that is important to understand, that between artificial intelligence and data science. Data science is the process and method for extracting knowledge and insights from large volumes of disparate data. It's an interdisciplinary field involving mathematics, statistical analysis, data visualization, machine learning, and more. It's what makes it possible for us to appropriate information, see patterns, find meaning from large volumes of data, and use it to make decisions that drive business. Data science can use many of the AI techniques to derive insight from data. For example, it could use machine learning algorithms and even deep learning models to extract meaning and draw inferences from data. There is some intersection between AI and data science, but one is not a subset of the other. Rather, data science is a broad term that encompasses the entire data processing methodology, while AI includes everything that allows computers to learn how to solve problems and make intelligent decisions. And both AI and data science can involve the use of big data, that is, significantly large volumes of data. In the next few lessons, the terms machine learning, deep learning, and neural networks will be discussed in more detail. Machine learning, a subset of AI, uses computer algorithms to analyze data and make intelligent decisions based on what it has learned. Instead of following rules-based algorithms, machine learning builds models to classify and make predictions from data. Let's understand this by exploring a problem we may be able to tackle with machine learning. What if we wanted to determine whether a heart can fail? Is this something we can solve with machine learning? The answer is yes. Let's say we are given data such as beats per minute, body mass index, age, sex, and the result, whether the heart has failed or not. With machine learning, given this dataset, we are able to learn and create a model that, given inputs, will predict results. So what is the difference between this and using a statistical analysis to create an algorithm? An algorithm is a mathematical technique. With traditional programming, we take data and rules and use these to develop an algorithm that will give us an answer. In the previous example, if we were using a traditional algorithm, we would take the data, such as beats per minute and BMI, and use this data to create an algorithm that will determine whether the heart will fail or not. Essentially, it would be an if-then-else statement. When we submit inputs, we get answers based on what the algorithm we determined is, and this algorithm will not change. Machine learning, on the other hand, takes data and answers and creates the algorithm. Instead of getting answers in the end, we already have the answers. What we get is a set of rules that determine what the machine learning model will be. The model determines the rules and the if-then-else statement when it gets the inputs. Essentially, what the model does is determine what the parameters are in a traditional algorithm, and instead of deciding arbitrarily that beats per minute plus BMI equals a certain result, we use the model to determine what the logic will be. This model, unlike a traditional algorithm, can be continuously trained and be used in the future to predict values. Machine learning relies on defining behavioral rules by examining and comparing large data sets to find common patterns. For instance, we can provide a machine learning program with a large volume of pictures of birds and train the model to return the label bird whenever it is provided a picture of a bird. We can also create a label for cat and provide pictures of cats to train on. When the machine model is shown a picture of a cat or a bird, it will label the picture with some level of confidence. This type of machine learning is called supervised learning, where an algorithm is trained on human-labeled data. The more samples you provide a supervised learning algorithm, the more precise it becomes in classifying new data. Unsupervised learning, another type of machine language, relies on giving the algorithm unlabeled data and letting it find patterns by itself. You provide the input, but not labels, and let the machine infer qualities. The algorithm ingests unlabeled data, draws inferences, and finds patterns. This type of learning can be useful for clustering data, where data is grouped according to how similar it is to its neighbors and dissimilar to everything else. Once the data is clustered, different techniques can be used to explore that data and look for patterns. For instance, you provide a machine learning algorithm with a constant stream of network traffic and let it independently learn the baseline, normal network activity, as well as the outlier and possibly malicious behavior happening on the network. The third type of machine learning algorithm, reinforcement learning, relies on providing a machine learning algorithm with a set of rules and constraints and letting it learn how to achieve its goals. You define the state, the desired goal, allowed actions, and constraints. The algorithm figures out how to achieve the goal by trying different combinations of allowed actions and is rewarded or punished depending on whether the decision was a good one. The algorithm tries its best to maximize its rewards within the constraints provided. You could use reinforcement learning to teach a machine to play chess or navigate an obstacle course. A machine learning model is the algorithm used to find patterns in the data without the programmer having to explicitly program these patterns. Machine learning is a broad field, and we can split it up into 3 different categories: supervised learning, unsupervised learning, and reinforcement learning. There are many different tasks we can solve with these. Supervised learning refers to when we have class labels in the dataset, and we use these to build the classification model. What this means is when we receive data, it has labels that say what the data represents. In a previous example, we had a table with labels such as age or sex. With unsupervised learning, we don't have class labels, and we must discover class labels from unstructured data. This could involve things such as deep learning looking at pictures to train models. Things like this are typically done with something called clustering. Reinforcement learning is a different subset, and what this does is it uses a reward function to penalize bad actions or reward good actions. Breaking down supervised learning, we can split it up into 3 categories: regression, classification, and neural networks. Regression models are built by looking at the relationships between features X and the result Y, where Y is a continuous variable. Essentially, regression estimates continuous values. Neural networks refer to structures that imitate the structure of the human brain. Classification, on the other hand, focuses on discrete values it identifies. We can assign discrete class labels, Y, based on many input features, X. In a previous example, given a set of features X, like beats per minute, body mass index, age, and sex, the algorithm classifies the output Y as 2 categories, true or false, predicting whether the heart will fail or not. In other classification models, we can classify results into more than 2 categories. For example, predicting whether a recipe is for an Indian, Chinese, Japanese, or Thai dish. Some forms of classification include decision trees, support vector machines, logistic regression, and random forests. With classification, we can extract features from the data. The features in this example would be beats per minute or age. Features are distinctive properties of input patterns that help in determining the output categories or classes of output. Each column is a feature and each row is a data point. Classification is the process of predicting the class of given data points. Our classifier uses some training data to understand how given input variables relate to that class. What exactly do we mean by training? Training refers to using a learning algorithm to determine and develop the parameters of your model. While there are many algorithms to do this, in layman's terms, if you are training a model to predict whether the heart will fail or not, that is, true or false values, you will be showing the algorithm some real-life data labeled true, then showing the algorithm again some data labeled false. And you will be repeating this process with data having true or false values, that is, whether the heart actually failed or not. The algorithm modifies internal values until it has learned to tell from data that indicates heart failure, that is true, or not, that is false. With machine learning, we typically take a data set and split it into 3 sets: training, validation, and test sets. The training subset is the data used to train the algorithm. The validation subset is used to validate our results and fine-tune the algorithm's parameters. And the testing data is the data the model has never seen before and used to evaluate how good our model is. We can then indicate how good the model is using terms like accuracy, precision, and recall. While machine learning is a subset of artificial intelligence, deep learning is a specialized subset of machine learning. Deep learning layers algorithms to create a neural network, an artificial replication of the structure and functionality of the brain, enabling AI systems to continuously learn on the job and improve the quality and accuracy of results. This is what enables these systems to learn from unstructured data, such as photos, videos, and audio files. Deep learning, for example, enables natural language understanding capabilities of AI systems and allows them to work out the context and intent of what is being conveyed. Deep learning algorithms do not directly map input to output. Instead, they rely on several layers of processing units. Each layer passes its output to the next layer, which processes it and passes it to the next. The many layers is why it's called deep learning. When creating deep learning algorithms, developers and engineers configure the number of layers and the type of functions that connect the outputs of each layer to the inputs of the next. Then, they train the model by providing it with lots of annotated examples. For instance, you give a deep learning algorithm thousands of images and labels that correspond to the content of each image. The algorithm will run those examples through its layered neural network and adjust the weights of the variables in each layer of the neural network to be able to detect the common patterns that define the images with similar labels. Deep learning fixes one of the major problems present in older generations of learning algorithms. While the efficiency and performance of machine learning algorithms plateau as the datasets grow, deep learning algorithms continue to improve as they are fed more data. Deep learning has proven to be very efficient at various tasks, including image captioning, voice recognition and transcription, facial recognition, medical imaging, and language translation. Deep learning is also one of the main components of driverless cars.
So can you talk about the different areas or categories of artificial intelligence?
Now, there are lots of different fields that AI works in, but if I were to, on a very, very high level, group some of the major areas where artificial intelligence is applied, I'd like to start off with natural language. Because natural language is, I'd say, the most complex data for machine learning to work with. If you see all sorts of data, whether that be a sequenced genome, whether that be audio, whether that be images, there's some sort of discernible pattern. There's some sort of, yes, this is what a car sounds like, or yes, this is what human voice sounds like. But natural language is fundamentally a very human task. It's a very human data source. We as humans invented it for humans to understand. If I were to, for example, give you a book title, there's actually a very, very famous book, and the title of the book is "There Are Two Mistakes in the title of this book." Now, there's actually only one mistake. There are two thes. The human brain doesn't realize that. What's the second mistake? That there was only one mistake. So this is the sort of natural language complexity that's involved here. Humans don't view natural language literally. We view it conceptually. If I were to write a 3 instead of an E, you would understand it because we don't mean the 3 in a literal sense. We mean that in a symbolic sense to represent the concept of E. And you can contextualize that 3 to figure out that, yeah, it means an E and not an actual 3. These are things that computers aren't capable of. So natural language is the #1 sort of field that I'm most interested in when it comes to machine learning. Second, I'd say the most popular would be visual data understanding, computer vision, because it enables us to do so many things. I mean, as humans, our primary sense is vision. In fact, a vast majority of your brain's processing power at any given moment goes to understanding what it is that you're seeing, whether it be a person's face, or whether it be a computer, or some text, or anything of that sort. And third, I would say audio-based data. So text-to-speech, speech-to-text, these are very, very complex. And the reason it's complex is because it kind of combines a lot of challenges into one. First of all, you've got to support many languages. You can't just support English and call it a day. You've got to support the other languages. You've got to support other demographics. And another challenge is that even within languages, there are absolutely infinite number of ways that any human could represent a language. Everyone's going to have a different accent. Everyone's going to have a different way of pronouncing certain words. There's no standardized way that every human will pronounce ice cube exactly like ice cube. That doesn't exist. And if you take a look at another challenge, it's that audio data is fundamentally very, very difficult to work with. Because the thing is, audio data exists in the natural world. What is audio? It's vibrations of air molecules. And vibrations of air molecules are fast. And audio is recorded at over, say, 44 kilohertz. That's a lot of data. 44,000 data points every single second. There are usually only 44,000 data points in an individual low-resolution image. So, of course, there are lots of challenges to work around when it comes to audio. But companies like IBM, Google, Microsoft have actually worked around these challenges, and they're working towards creating different services to make it easier for developers. So again, on a very, very high level, there's natural language understanding, there's computer vision, there's audio data, and of course there's the traditional set of tabular data understanding, which is essentially structured data understanding.
Some of the most common application areas of AI include natural language processing, speech, and computer vision. Now, let's look at each of these in turn. Humans have the most advanced method of communication, which is known as natural language. While humans can use computers to send voice and text messages to each other, computers do not innately know how to process natural language. Natural language processing is a subset of artificial intelligence that enables computers to understand the meaning of human language. Natural language processing uses machine learning and deep learning algorithms to discern a word's semantic meaning. It does this by deconstructing sentences grammatically, relationally, and structurally, and understanding the context of use. For instance, based on the context of a conversation, NLP can determine if the word cloud is a reference to cloud computing or the massive condensed water vapor floating in the sky. NLP systems might also be able to understand intent and emotion, such as whether you are asking a question out of frustration, confusion, or irritation. Understanding the real intent of the user's language, NLP systems draw inferences through a broad array of linguistic models and algorithms. Natural language processing is broken down into many subcategories related to audio and visual tasks. For computers to communicate in natural language, they need to be able to convert speech into text, so communication is more natural and easy to process. They also need to be able to convert text to speech, so users can interact with computers without the requirement to stare at a screen. The older iterations of speech-to-text technology required programmers to go through a tedious process of discovering and codifying the rules of classifying and converting voice samples into text. With neural networks, instead of coding the rules, you provide voice samples and their corresponding text. The neural network finds the common patterns among the pronunciation of words and then learns to map new voice recordings to their corresponding texts. These advances in speech-to-text technology are the reason we have real-time transcription. Google uses AI-powered speech-to-text in their call screen feature to handle scam calls and show you the text of the person speaking in real time. YouTube uses this to provide automated closed captioning. The flip side of speech-to-text is text-to-speech, also known as speech synthesis. In the past, the creation of a voice model required hundreds of hours of coding. Now, with the help of neural networks, synthesizing human voice has become possible. First, a neural network ingests numerous samples of a person's voice until it can tell whether a new voice sample belongs to the same person. Then, a second neural network generates audio data and runs it through the first network to see if it validates it as belonging to the subject. If it does not, the generator corrects its sample and reruns it through the classifier. The two networks repeat the process until they generate samples that sound natural. Companies use AI-powered voice synthesis to enhance customer experience and give their brands their unique voice. In the medical field, this technology is helping ALS patients regain their true voice instead of using a computerized voice. The field of computer vision focuses on replicating parts of the complexity of the human visual system and enabling computers to identify and process objects in images and videos in the same way humans do. Computer vision is one of the technologies that enables the digital world to interact with the physical world. The field of computer vision has taken great leaps in recent years and surpasses humans in tasks related to detecting and labeling objects, thanks to advances in deep learning and neural networks. This technology enables self-driving cars to make sense of their surroundings. It plays a vital role in facial recognition applications, allowing computers to match images of people's faces to their identities. It also plays a crucial role in augmented and mixed reality, the technology that allows computing devices, such as smartphones, tablets, and smart glasses, to overlay and embed virtual objects on real-world imagery. Online photo libraries like Google Photos use computer vision to detect objects and classify images by the type of content they contain.
Can you tell us a little bit about the work you're doing with self-driving cars?
I've been working on self-driving cars for the last few years. It's a domain that's exploded, obviously, in interest since early competitions back in the 2005 domain. And what we've been working on really is putting together our own self-driving vehicle that was able to drive on public roads in the region of Waterloo last August. With the self-driving cars area, one of our key research domains is in 3D object detection. So this remains a challenging task for algorithms to perform automatically, trying to identify every vehicle, every pedestrian, every sign that's in a driving environment so that the vehicle can make the correct decisions about how it should move and interact with those vehicles. And so we work extensively on how we take in laser data and vision data and radar data and then fuse that into a complete view of the world around the vehicle.
When we think of computer vision, we usually think immediately of self-driving cars. And why is that? Well, it's because, it's hard to pay attention when driving on the road, right? You can't, both be looking at your smartphone and also be looking at the road at the same time. Of course, it's sometimes hard to predict what people are going to be doing on the street as well when they're crossing the street with their bike or skateboard or whatnot. So it's great when we have some sort of camera or sensor that can help us detect these things and prevent accidents before they could potentially occur. And that's one of the limitations of human vision is visual attention. So I could be looking at you, Rav, but behind you could be this delicious slice of pizza. But I can only pay attention to one or just some limited number of things at a time. But I can't attend to everything in my visual field all at once at the same time, like a camera could, or like how computer vision could potentially do so. And so that's one of the great things that cameras and computer vision is good for, helping us pay attention to the whole world around us without having us to look around and make sure that we're paying attention to everything. And that's just in self-driving cars. So I think we all kind of have a good sense of how that shapes, how AI and computer vision shapes the driving and transportation industry.
Well, self-driving cars are certainly the future. And there's tremendous interest right now in self-driving vehicles, in part because of their potential to really change the way our society works and operates. I'm very excited about being able to get into a self-driving car and read or sit on the phone on the way to work instead of having to pilot through Toronto traffic. So I think they represent a really exciting step forward. But there's still lots to do. We still have lots of interesting challenges to solve in the self-driving space before we have really robust and safe cars that are able to drive themselves 100% of the time autonomously on our roads.
We've just launched our own self-driving car specialization on Coursera, and we'd be really happy to see students in this specialization also come and learn more about self-driving. It's a wonderful starting point. It gives you a really nice perspective on the different components of the self-driving software stack and how it actually works. So everywhere from how it perceives the environment, how it makes decisions and plans its way through that environment, to how it controls the vehicle and makes sure it executes those plans safely. So you'll get a nice broad sweep of all of those things from that specialization. And from there, you then want to become really good and really deep in one particular area if you want to work in this domain. Because again, there's so many layers behind this. There's so much foundational knowledge you need to start contributing that you can't go wrong. If you find something interesting, just go after it. And I'm sure there'll be companies that will need you for this.
Welcome to Exploring AI and Ethics. In this video, you will learn about what AI ethics is and why it matters. You will find out what makes AI ethics a socio-technical challenge, what it means to build and use AI ethically, and how organizations can put AI ethics into action.
AI, artificial intelligence, is very pervasive in everybody's life. Even if often we don't realize it, we use it when we use a credit card to buy something online, when we search something on the web, when we post or like or follow somebody on a social platform, and even when we drive with the navigation support and the driver assistance capabilities of the car based on AI. This pervasiveness generates very fast and significant transformations in our life and also in the structure and equilibria of our society. This is why AI, besides being a technical and scientific discipline, has also a very significant social impact. This raises a lot of ethical questions about how AI should be designed, developed, deployed, used, and also regulated. The socio-technical dimensions of AI requires efforts to identify all stakeholders that go well beyond technical experts and include also sociologists, philosophers, economists, policymakers, and all the communities that are impacted by the deployment of this technology. Inclusiveness is necessary in defining the ecosystem, in all the phases of the AI development and deployment, and also in the impact of AI in the deployment scenario. Without it, we risk of creating AI only for some and leave many others behind in a disadvantaged position. Everybody needs to be involved in defining the vision of the future that we want to build, using AI and other technology as a means and not as an end. To achieve this, appropriate guidelines are necessary to drive the creation and use of AI in the right direction. Technical tools are necessary and useful, but they should be complemented by principles, guardrails, well-defined processes, and effective governance. We should not think that all this slows down innovation. Think about traffic rules. It may seem that traffic lights, precedents and stop signals and speed limits are slowing us down. However, without them, we would not drive faster, but actually we would drive much slower because we would be always in a complete state of uncertainty about other vehicles and pedestrians. AI ethics identifies and addresses the socio-technical issues raised by this technology and makes sure that the right kind of innovation is supported and facilitated so that the path to the future we want is faster.
As our CEO at IBM states, trust is our license to operate. We've earned this trust through our policies, programs, partnerships, and advocacy of the responsible use of technology. For over 100 years, IBM has been at the forefront of innovation that brings benefits to our clients and society. This approach most definitely applies to the development, use, and deployment of AI. Therefore, ethics should be embedded into the life cycle of the design and development process. Ethical decision-making is not just a technical problem-solving approach. Rather, an ethical, sociological, technical, and human-centered approach should be embarked upon, based on principles, values, standards, laws, and benefits to society. So having this foundation is important, even necessary, but where to start? A good place to start is with a set of guiding principles. At IBM, we call our principles the principles of trust and transparency, of which there are 3. The purpose of AI is to augment, not replace human intelligence. Data and insights belong to their creator, and new technology, including AI systems, must be transparent and explainable. This last principle is built upon our pillars, of which there are 5. We just mentioned transparency, which reinforces trust by sharing the what and the how the AI is being used for. It must be explainable and also fair, so when it's properly calibrated, it can assist in making better choices. It should be robust, which means it should be secure, and as well as privacy preserving, safeguarding privacy and rights. We know having principles and pillars are not enough. We have an extensive set of tools and talented practitioners that can help diagnose, monitor, promote all of our pillars and continuous monitoring to mitigate against drift and unintended consequences.
The first step to putting AI ethics into action, just like with anything else, is about building understanding and awareness. This is about equipping your teams to think about AI ethics, what it means to put it into action, whatever solution you're building and deploying. Let's take an example. If you're building a learning solution and deploying that within a company, your HR team leader who's doing that should be thinking about, is this solution designed with users in mind? Have you co-created the solution with users? How does it enable equal access to opportunity to all the employees across diverse groups? A keen understanding of AI ethics and reflecting on these issues continuously is critical as a foundation to putting AI ethics into action. The second step in putting AI ethics into action, once you build that understanding and awareness and everybody is reflecting on this topic, is to put in place a governance structure. And the critical point here is it's a governance structure to scale AI ethics in action. It's not about doing it in one isolated instance in a market or in a business unit. It's about a governance structure that works at scale. So we talked about understanding and awareness as a foundation. Second, governance, which is the responsibility of leaders to put in place structures. Once you've got these two elements, the third step is operationalizing. How do you make sure a developer or a data scientist or a vendor who's in Malaysia or Poland knows how to put AI ethics into action, and what does it mean for them, right? It's one thing to put structures in place at the global level, but how do you make sure it's operationalized at scale in the markets, and every user, every data scientist, every developer knows what they need to do? This is all about having clarity of the pillars of trustworthy AI. For IBM, it is transparency. Let's go back to our learning example. Are you designing it with users? Think about what we think of as best-in-class transparent recommendation systems, your favorite movie streaming service or your cab hailing service. It's transparent. Is it explainable? Is it telling you what recommendations are and why they're being made? But also telling you as a user, it's your choice to make the final decision. Fairness, is it giving equal access to opportunity to everyone by ensuring adoption, not just of the process, but also the outcome across different groups? Robustness, privacy. Every data scientist and developer and every vendor needs to know what we mean by these in a very operational manner.
Welcome to Understanding Bias in AI. In this video, you will learn about bias in the context of AI. You will find out how bias can emerge in AI, how bias can impact AI's outcomes, and how to begin mitigating potential bias in AI.
So bias in artificial intelligence is all about unwanted behaviors where AI systems that are used in consequential decision-making tasks, whether it's in lending, hiring, even in criminal justice, give systematic disadvantages to certain groups and individuals. So an example would be an AI system that's helping make decisions on who should receive extra preventative health care, and it gives more of that to white people than Black people. Or another example is hiring algorithm, where the AI system actually gives more qualified men a chance to interview than qualified women. There's actually many sources of this happening. So when we talk about AI or machine learning systems, they're trained on historical decisions that human decision makers have made in the past. So because of that, there's actually the possibility that the human decision makers in the past were implicitly or explicitly biased themselves, and so that's reflected in the training data through prejudice. Second is through the sampling of the data. So it's possible that certain groups are overrepresented or underrepresented in a particular data set. Another aspect that's sometimes overlooked is in the data processing or data preparation phase in a data science project. So even the fact that I do some feature engineering can lead to additional biases that might not have been there before. So an example of that is coming back to our healthcare example. So if I look at healthcare costs separately as a feature, so inpatient, outpatient, or emergency room, then there's much less bias that's introduced against African Americans. Whereas if I combine all of those into a single feature, it's actually much more bias against African Americans. Okay. And then there's also the question of how am I even posing the problem itself? So maybe I'm predicting the wrong thing. So if I'm trying to predict criminality or future crimes, then arrests is not a good way to look at that, because the police arrest people more often where they're more active in certain neighborhoods, and being arrested is not the same as being guilty. So as we talked about, there's many sources of those biases, and so we need to take actions that help undo those sources. So one important aspect of it is even recognizing that there are biases. So having a team of people who have diverse lived experiences is one way to recognize those harms and other sort of biases that might be in play. Another thing is to search for data sets that actually have fewer biases themselves. So that's another way to counteract biases. And then finally, there's technical approaches. So if we have a machine learning model that we're training on data that is biased, we can actually introduce extra constraints or other sort of statistical measures in order to mitigate biases. So we've developed several such algorithms, and many of them are available in the open source toolkit named AI Fairness Thesis.
Our goal is to ensure our technology makes a positive impact on society. I am proud to be a member of the IBM AI Ethics Board to focus on conscious inclusion through good tech. Our AI Ethics Board represents a cross-section of diverse IBMers who address and research eliminating bias while establishing standards in this space. A few ways in which IBMers use AI and data skills is by leveraging our technology to develop assets to address bias. Also to address inclusive language and tech terminology. This is around our Language Matters initiative. And to ensure testing of our solutions to decrease the probability and minimize the potential for bias. In D&I, we use AI and data analytics and insights to inform decision support and address as well as minimize the potential for bias. In HR, this means enhancing decision support that can inform pay and retention, hiring, and promotion decisions. Using AI and data insights plays an important role to assist in our compliance requirements and proactive actions that we take around the globe.
Welcome to AI Ethics and Regulations. In this video, you will learn about what an AI regulation is, how AI regulations connect with AI ethics, and why it's important to understand AI regulations if you work with AI.
A regulation is a government rule enforceable by law. The landscape of regulations around AI is evolving rapidly, and it's important to understand key pieces of regulation in order to design, develop, and deploy and use AI legally and ethically.
IBM's position is that we call for precision regulation of artificial intelligence, and we support targeted policies that would increase the responsibilities for companies to develop and operate trustworthy AI. Precision regulation of AI refers to a regulation that aims to be risk-based, context-specific, and which allocates responsibility to the party that is closest to the risk, which might shift throughout the AI lifecycle.
Specifically, IBM has proposed a precision regulation framework that incorporates 5 policy imperatives for organizations that provide and/or use AI systems. First, designate an AI ethics official, a lead official responsible for compliance with trustworthy AI. Develop different rules for different risks. In other words, regulate AI in context, not the technology itself. Don't hide your AI, make it transparent. Explain your AI. So in other words, make it explainable, not a black box decision. And test your AI for bias.
Welcome to AI Ethics, Governance, and ESG. In this video, you will learn about what AI governance is and what it accomplishes, what ESG is and what it accomplishes, and how governance and ESG connect to AI ethics.
Governance is the organization's act of governing through its corporate instructions, staff, its processes, and its systems to direct, evaluate, and monitor, and to take corrective action throughout the AI lifecycle to provide assurance that an AI system is operating as an organization intends it to, and as its stakeholders expect it to, and as may be required by relevant regulation. The objective of governance is to deliver trustworthy AI by establishing requirements for accountability, responsibility, and oversight. Governance provides many benefits, including, for example, trust. When AI activities are aligned with values, organizations can build systems that are transparent, fair, and trustworthy, boosting client satisfaction and brand reputation. Another benefit is efficiency. When AI activities are standardized and optimized, development can happen with greater efficiency, accelerating time to market. And compliance. When AI activities are already managed and monitored, adjusting them to align with new and forthcoming industry regulations and legal requirements is really less cumbersome. A successful governance program takes into account people, processes, and tools. It clearly defines the roles and responsibilities of people in building and managing trustworthy AI, including leaders who will set policies and establish accountability. It establishes processes for building, managing, monitoring, and communicating about AI, and it leverages tools to gain greater visibility and consistency into AI system performance throughout the AI lifecycle.
ESG stands for Environmental Social Governance, and these are factors that are used to measure all non-financial risks and opportunities at companies. At IBM, that translates into IBM Impact, our strategy and philosophy on ESG. IBM Impact is comprised of 3 pillars that we believe will create a more sustainable future. These pillars are environmental impact, equitable impact, and ethical impact. And we accomplish this by making a lasting positive impact in the world in business ethics, our environment, and in the communities in which we work and live. The governance aspect of ESG pertains to creating innovations, policies, and practices that prioritize ethics, trust, transparency, and above all, accountability. And AI ethics is a significant aspect of our governance initiatives. For example, in 2022, we're aiming to reach 1,000 ecosystem partners trained in tech ethics. This goal matters because we believe the benefits of AI should touch the many and not just the few. And developing a culture of trustworthy AI must happen everywhere, not just within IBM. We're leading the way in AI ethics as we aspire to create a more ethical future.
The original AI researchers were very interested in games because they were extremely complex. Huge numbers of possible positions in games were available. Yet they're simple in a certain way. They're simple in that the moves are well-defined, the goals are well-defined, and so you don't have to solve everything all at once.
With chess in particular, and the work on Deep Blue at IBM, what became apparent, what computers could do on a problem like that, was bring a massive amount of compute resource to do deeper searches, to investigate more options of moves in chess that than was previously possible. Watson defeating Jeopardy, so this was another crossover point in sort of the development of AI and cognitive computing. The questions that IBM was able to answer with Jeopardy were questions that weren't simply looking up in a database and finding the answer somewhere. Rather, it required information retrieval over lots of different information resources, and then the combining of these together using machine learning that could arrive at answers that went beyond what was simply written somewhere.
Now our technology is so much better and so much more advanced that we're really ready to move on and to tackle much more challenging problems that have this kind of ill-defined or kind of messy nature.
Every industry, from oil and gas to healthcare to media and entertainment to retail, are just being swamped by a tsunami of unstructured data. That can be multimedia, it can be images, it can be video, it can be text. And it's really the ability to understand that data that is becoming critical.
One of the most valuable applications of cognitive computing is in the health domain. Medical providers, physicians, nurses, assistants face enormous challenges leveraging all of the available information that's out there. The medical literature increases by about 700,000 articles every year. And there's already millions of journal articles out there, and today's imaging technologies produce very rich amounts of information. In fact, a particular scan might have 5,000 images in it. You combine the image analysis with natural language understanding and text analysis, leveraging the medical literature, leveraging the patient's medical history. The physician has got a lot more information and knowledge at their disposal to help them make the best diagnosis possible.
Clearly, there's this intersection of what the computer can do and what people are able to do that gives you something that's better than each of them individually. What is going to be truly interesting is to see what is the best way for them to have really symbiotic type of interaction, taking advantage of each other's strengths to collectively solve a problem.
Watson, it looks at another aspect of intelligence and a much more difficult aspect of intelligence, that is language. You have to be able to interpret the questions and come up with the right answers, no matter what the topic. So I think the ideal scenario for AI in the modern world is not to try and develop a system that completely autonomously handles every aspect of a problem, but have a collaboration between machines doing what they do best and people doing what they do best. And I can imagine that combination will do better than either one by themselves. We're constantly here looking for what's the next grand challenge problem that we can take on that's not just around the corner or a year away, but it's going to take a multi-year effort, and when we get there, we'll have something that's valuable for the world.
What does AI have in store for us in the future?
My crystal ball is a little cloudy, so I don't know if I have a prediction that I would bet money on. What I do know is what we have seen is the way AI has progressed. It starts fairly slowly, but then it gains steam exponentially. One good example is DeepMind put the system together that won in the game of Go. It's a 2,500-year-old game which won against a human opponent. But what's most amazing is while the first system was able to outdo 2,500 years of human history in the game, the second generation of that system was able to outplay the first generation of the system in less than 1 year. And it only took about 40 hours of training for it to be able to achieve that level of proficiency in that game. And it won 100 games out of 100. So what we do know is the pace of which this technology is accelerating is just breathtaking, and it's not something we can predict very well. So if it was one prediction I were to make, it's going to get faster, it's going to get better, it's going to get cheaper, and it is going to happen very, very rapidly, within a very short period of time.
It's going to be an interesting world. It's going to evolve very rapidly because these technologies not only can perform tasks that we've never seen automated before, but learn as they do them and continue to improve. So what we'll see is we'll deploy systems, and every year they'll get incrementally better at the tasks they're trying to do. So we won't have to drive our own cars anymore. Hopefully we won't have to put away our own dishes. There'll be a lot of simple things in our lives that become automated and become eliminated from our daily task list. It's a revolution that we've been through before. The first washing machines, the first dishwashers, etc. All these things have helped us to enriched our lives and simplified the way we live and increased our comfort. And I think we'll see many more such evolutions as we watch the AI world unfold.
Particularly in healthcare, I think we'll see faster recovery times. We'll see better patient outcomes. We'll see people spending less money and time in hospitals and in various care centers. AI has been game-changing for healthcare. There's so much information that we can take out of a particular system and apply it to another. We can build all sorts of models that have been, that can be hugely beneficial to long-term care. So that's something that I'm very excited about and seeing that evolve.
Looking into the crystal ball, I'm always apprehensive to make long-term predictions, but my hope is that we are able to indeed deploy these collaborative robotic systems, including self-driving cars, to make people's lives better. That's the idea, is to use AI and robotics technology to improve the quality of life for the whole spectrum of society. So I would be looking forward to a future in which AI plays a central role in freeing us from the dull, the mundane, the dirty, the dangerous jobs, and hopefully providing us with more time to spend with our families, better health, potentially, better health care through data analysis. And so I think if I envision the future that I hope will come to pass in a number of years, we'll be really leveraging these technologies to make our lives better and to free ourselves from dull, dirty, dangerous work.
In a world
What advice would you give to someone who wants to learn AI or perhaps even get into a career in AI?
So I believe artificial intelligence is going to permeate every sphere of human endeavor. So the first thing I would say is I would congratulate the person who's chosen to study and apply AI as having made the right choice. The second part I would say is because the technology is moving so fast, because we have not yet discovered what we're gonna discover, I think it's really important to keep an open mind. It's important to keep an open mind and not get too attached to any particular technology, any particular technique, any particular implementation, but to really think forward and think outside of the box and think about, think about the art of the possible, think about what may come. And the number one advice I would give is apply what you learn. Don't make it academic, make it practical.
The first thing I would say is take a look at a great Coursera course like this one and grasp the basics of AI. get a fundamental lay of the land and understand what is involved in various types of AI systems, and perhaps find the niche that you're most interested in. And then, of course, look at academic programs that can help you to learn more about that specific area. And for students who are coming up through high school, for example, I would say definitely spend time focusing on math and science. Certainly all disciplines are valuable, but your knowledge of mathematics and science will certainly pay off when you're working on AI systems, because there are tons of opportunities, and you'll need mathematics to really fully understand how the AI systems operate. So take your mathematics and your science seriously, and then look at Coursera, and then beyond to other educational programs that can give you the basis you need to really jump into the industry.
The field of AI has changed a lot in the last 5 years. You no longer require a PhD in some kind of advanced mathematics or know some obscure programming language. You just have to know how to use the software APIs and understand the problem. For example, you can use Watson, and you just have to understand the problem and understand how the API works. But you still require some advanced knowledge if you would like to build your own algorithm.
So artificial intelligence, machine learning, this is a very important field. It is the future of technology because it essentially opens up this whole new world of interaction with computers. A world that so far we barely even knew existed. It enables us to interact with computers in an implicit way. But what I would say is that while machine learning technology is important, it's not something that you can learn in isolation. Machine learning technology is not its own standalone subject. It's another algorithm in the toolbox of a plethora of algorithms that programmers will use in their applications. Albeit a much more intelligent or a much more powerful algorithm than most, but still, it's another algorithm. So before you learn machine learning technology, it's very important to understand the actual programming and the technology that goes behind machine learning technology, specifically because machine learning actually requires this kind of next generation of programming, hardware acceleration, and so much more that regular programming and regular algorithms don't necessarily require. So I would really recommend making sure that, first of all, you are passionate about technology itself. If you are, continue. Learn about programming, learn about coding, learn how to actually speak the computer's language, learn about the computational thinking behind code, and then go ahead and learn about machine learning from the very, very basics. Start off with an API like IBM Watson to help you get an idea of what it's capable of, and then move on to more advanced custom techniques and the math behind them.
So AI is a fascinating field, but it's built on a huge number of foundational domains or foundational fields of study. So you really need to know your mathematics, you really need to know your probability theory and statistics, your optimization, and you have to be able to program. You have to be able to take advantage of the tools that are out there to train these networks and understand how they work. So AI is a really broad field that requires a lot of specialists and a lot of specialization in different areas. So one of the best things you can do is to get started quickly. Start playing with some simple tasks. Try to identify digits or try to find cats on internet pictures, right? Things like this. These are wonderful challenges that can get you going and understanding what you need to learn about that field.
Getting into AI now is like getting into anything to do with internet, 20, 30 years ago. It's kind of the renaissance of software right now. It's possible now. It wasn't possible 10 years ago. We have the computing technology, we have the computing power, we have the knowledge, and this is a field that will only grow. So I think you need to get in yesterday.
My latest poll of top cities for AI, which is primarily myself just looking at what's coming through my own inbox in terms of opportunities, it's fairly widespread, actually. There are a lot of opportunities in a lot of different places. So there's, of course, the San Francisco Bay Area. which continues to be a hotbed for startups in AI and robotics, and I think will continue to develop. There's Boston in the United States, which also has a large number of startups. There's Seattle. And then here in Canada, we've been doing a great job in both Toronto and Montreal of actually developing quite a robust and thriving AI ecosystem that I think is going to also continue to develop and grow. So I think we're quite excited about that. And then farther afield, there are a number of locations in Europe, Asia, some opportunities in China, certainly, China and India as well, absolutely. So lots of, if you're located somewhere next to a major city center, I think in any of these areas, you're well positioned to launch your AI career.
Toronto is exploding. It's been amazing to watch and be a part of. You know, we have Geoffrey Hinton, obviously, one of the 3 pillars of you know, the Turing Award for the major contributions in deep learning, and the whole Vector Institute and ecosystem has come up around the wonderful progress that came out of the University of Toronto over the last few decades. And so what we're seeing is wonderful incubators and startups in the area, you know, investing heavily in AI technology and capabilities. We're seeing large companies bringing in research labs and putting those right next to the university. And we're seeing, you know, a wonderful amount of funding coming in for research specifically in AI in Toronto. So I think we're competitive with any of the best places to learn and work on AI in the world.
I think Canada is actually doing very well. We've done an excellent job overall in terms of centralizing some really fantastic AI talent. So in Toronto and Montreal in particular, and also in Vancouver, but Vancouver, Edmonton, a number of different cities in Canada have really become very strong AI centers. And they continue to grow. And we're attracting a lot of great AI talent. And I believe that will just continue. So Canada is shaping up to be a great place to come and do AI research and work in AI.
So what advice would you give to someone who's looking to get into a career in AI?
Yeah, absolutely. I had a bit of an unusual route becoming a data scientist or an AI specialist myself. I have a background in psychology. So when I was studying, I was basically thinking of continuing to do academic research and not go into industry. But at some point in time, I had a realization that I didn't really want to become a professor. I didn't really want to teach or do research in an academic setting. So I started looking for jobs, and it was quite difficult because what we see today is, you know, sometimes what you learn in university doesn't translate directly into what companies want. So how do you bridge that gap exactly? For me, when I was at the time still in Tokyo, Japan, I didn't have a lot of resources around me, well, English-speaking resources at the time, where I could develop my skills. So I looked towards online courses, and online courses helped me, you know, practice Python, practice R, my data analysis skills through programming, and I was able to develop a foundation in the skill set that was highly sought after by many different companies. And then from there, the question became, okay, now I have these skills, these newly developed skills through these courses that I've taken online. How do I translate that to something that I can show and demonstrate to potential employers? So then the next problem I had to deal with was, well, how do I demonstrate that some way? So I created a portfolio of different online assignments, exercises, projects to demonstrate that I could do, you know, the kinds of things that they were hoping that I could do to show my competency. I also, when I came back to Toronto, Canada, I started doing meetups to teach at these meetups, teach R, teach Python, teach data science, to again further demonstrate my competency so that people could really see that I could do what I was claiming that I could do, which was a little bit difficult because people would just look at my resume and just see, oh, you have a background in psychology. What does that have to do with, you know, data science or AI? So it was hard in that sense. That I had to overcome that burden of proof. Oh, and the final piece of advice that I would give is connect with fellow local AI specialists. So whether they're data scientists, a specialist in a particular field of AI, machine learning researchers, data engineers, just to get a better sense of what kind of AI specialists you might be interested in becoming. Because today there's so many different kinds of AI specialists. You could be very technical. You could be doing research on the latest state-of-the-art algorithms. Or you could be doing something a bit more business-oriented, like trying to optimize revenue, maybe some reporting as well, trying to find ways to personalize a particular service to each and every kind of user that you might have. There's different aspects of AI, and I think it's really important to have some clarity into what kind of role and what kind of job you want. And the first step to do that is to be able to reach out and ask questions to people who are already in the field. And it's a great way to get a sense and also maybe even form some connections that might be meaningful in your career as well. So those are the 4 things. Number 1 is, acquire skills wherever you can. Always be open to learning new things and new skills. Number 2 is demonstrate your capabilities through projects, exercises, something that you can share online, even blog posts and articles. Number 3, if you can, teach at meetups or maybe even more ideally conferences so you can demonstrate your competencies in public. And then number 4 is going to be try to connect with local experts or local specialists who are already in the field so you can get a better sense of what that career kind of roadmap might look like for you.